Here is a fact that surprises even some seasoned contractors. Concrete does not dry. If your concrete is drying, it is dying. Welcome to the hidden science of construction. Every time a foundation cracks, a driveway spalls, or a structural column fails a compressive strength test, the culprit is rarely the mix design. The mix was likely perfect when it left the batch plant. The failure happened in the critical hours and days that followed. The failure was a lack of proper curing. Many viewers decide whether to continue watching within the first 5 to 15 seconds. So let me give you the bottom line right now. Improperly cured concrete can lose up to 50% of its potential strength. 50%. That is the difference between a structure that lasts a century and one that crumbles in a decade. Today, we are going deep into the molecular battlefield of concrete hydration. We will uncover the real measurable strength differences between proper and improper curing. More importantly, we are going to look at the exact arsenal of professional testing equipment that engineers use to guarantee concrete reaches its maximum potential. We will break down how to use the Concrete Curing Box Cure, +3, the heavy-duty 165-quart heat and AC box, the economy thermocure box, curing tank heaters, circulators, and advanced moisture room control panels. If you are a materials tester, an engineer, or just someone who wants to understand the literal foundation of the modern world, you are in the right place. To understand why curing equipment is so vital, we first have to understand what concrete actually is. Concrete is a mixture of aggregates, sand, and gravel, bound together by Portland cement and water. When water meets cement, it does not act as a drying agent. It triggers a violent, exothermic chemical reaction called hydration. During hydration, the chemical compounds in the cement form microscopic, needle-like crystals called calcium silicate hydrate, or CSH. These crystals grow, interlock, and wrap around the sand and gravel, creating a dense, impenetrable matrix. This is what gives concrete its legendary compressive strength. But here is the catch. This crystalline growth takes time, and it absolutely requires continuous moisture and controlled temperatures. If concrete is left exposed to the sun, wind, or dry air, the water near the surface evaporates before the chemical reaction can finish. The hydration process stops dead in its tracks. The CSH crystals never fully form. When this happens, you get a surface that is weak, porous, and prone to dusting, where the top layer literally rubs away like chalk. Worse, the surface shrinks rapidly while the damp interior remains expanded, causing massive tensile stress that rips the concrete apart, resulting in plastic shrinkage cracking. Hydration is incredibly sensitive to temperature. If the environment is too cold, below 50 degrees Fahrenheit or 10 degrees Celsius, the chemical reaction goes dormant. The concrete will sit there, useless and weak. If it freezes, the water inside turns to ice, expanding and destroying the internal matrix from the inside out. Conversely, if the environment is too hot, the hydration reaction happens too fast. This creates a highly porous, disorganized microscopic structure that might show high early strength but will ultimately result in a drastically lower 28-day ultimate strength. So what is the real strength difference? Let's look at the engineering data. In civil engineering, concrete strength is typically measured at 28 days. Let's take a standard 4,000 pounds per square inch mix. If you take a test cylinder of that concrete and cure it perfectly, meaning you keep it at 100% relative humidity and a stable 73.4 degrees Fahrenheit, 23 degrees Celsius, as dictated by ASTM C31 standards, it will hit its 4,000 PSI target at 28 days. In fact, it will likely exceed it, and it will continue to gain strength for years. Now let's take that exact same mix and leave it outside in dry, 80-degree air. Day 3. The improperly cured concrete might look fine, but internally hydration has stalled. Day 7. The properly cured cylinder is at about 70% of its strength. The air-dried cylinder is already lagging by 20%. Day 28. The properly cured cylinder hits 4,000 pounds per square inch. The improperly cured cylinder will likely top out at around 2,000 to 2,500 pounds per square inch. You have lost half of your structural capacity simply because the water evaporated too fast. The concrete becomes highly permeable, meaning water, road salts, and chemicals can easily penetrate it later, rusting the internal steel rebar and causing concrete cancer. This is why on-site quality control is not just a suggestion, it is a legal and structural mandate. Engineers cast test cylinders on the job site to prove the concrete meets specifications. But if those test cylinders are left baking in the sun or freezing in the snow, they will fail the lab tests, causing massive delays and costing contractors thousands of dollars in rejected concrete. That is exactly why you need specialized field and lab equipment. Let's look at the products that prevent these catastrophic failures. To ensure that test cylinders represent the true potential of the concrete mix, the American Society for Testing and Materials, ASTM, mandates strict temperature and moisture controls for the first 48 hours of field curing. Here are the machines that make that possible. 1. Concrete Curing Box Cure +3. When you are on a busy construction site, you need a microenvironment that completely isolates your concrete samples from the chaos of the ambient weather. This is where the Concrete Curing Box Cure +3 shines. What it does, this is a highly advanced, portable, climate-controlled vault for your test cylinders. It is specifically engineered to maintain the strict ASTM required temperatures for initial field curing. How it works. The Cure +3 utilizes a digital temperature controller that automatically toggles between heating and cooling based on internal sensors. If the ambient temperature drops at night, the heating element kicks on. If the midday sun beats down, the cooling system takes over. Why you need it? It removes all human error. You simply place your 4x8 or 6x12 cylinders inside, set the digital thermostat, and walk away. The Cure +3 ensures that your samples are hydrating perfectly, providing an accurate, defendable representation of your concrete slab strength. 2. Concrete Curing Box 165 quarts heat/AC. For massive infrastructure projects, highways, or high-rise developments, you are pulling a lot of samples. You need serious volume and serious power. Enter the 165 quart heat/AC concrete curing box. What it does, this heavy-duty unit offers a massive 165 quart capacity, meaning it can hold a substantial number of test cylinders at once. It is built for extreme weather environments where standard coolers simply cannot keep up. How it works, this box features industrial-grade, built-in heating and air conditioning units. Unlike lighter models that might rely on basic thermoelectric cooling, this unit has the raw mechanical power to fight off blistering desert heat or freezing northern winters. Why you need it? When millions of dollars are on the line, you cannot afford a temperature fluctuation to ruin a batch of test cylinders. This box provides a rugged, job site-ready fortress that guarantees your high volume of samples remains in the precise temperature, Goldilocks zone, required for accurate lab testing later. 3. Economy Thermo-Cure Concrete Curing Box. Not every project has the budget of a federal highway, but every project still requires standard compliance. That is the exact use case for the Economy Thermo-Cure Concrete Curing Box. What it does, it provides reliable, ASTM-compliant initial field curing at a price point that makes sense for smaller contractors, independent testing labs, or projects in moderate climates. How it works, it features a robust, rust-proof plastic construction and operates on a simplified but highly effective thermostat system. While it may not have the extreme heavy-duty AC units of the larger models, it efficiently circulates water or air to maintain the necessary temperature gradient for standard concrete samples. Why you need it? It democratizes quality control. It allows smaller operations to maintain professional, compliant standards without breaking the bank, ensuring that even residential or light commercial pours are tested accurately. 4. Curing Tank Heater. Once those cylinders leave the job site in their curing boxes, they go to a testing laboratory for final curing until their 7-day or 28-day break tests. In the lab, cylinders are often submerged entirely in lime-saturated water tanks. But water temperature is critical. What it does, the curing tank heater is an industrial immersion heater designed to keep large reservoirs of water at the exact required 73.4 degrees Fahrenheit, 23 degrees Celsius. How it works. Submerged directly into the tank, it uses a sensitive thermostat to detect microscopic drops in water temperature. When the lab gets cold at night, the heating coil activates, gently warming the water to prevent the hydration process inside the submerged cylinders from slowing down. Why you need it? Without a reliable tank heater, the ambient air conditioning of a laboratory would eventually cool the water tank down, skewing the break strengths of every single cylinder in that tank and invalidating the lab's testing data. 5. Curing Tank Circulator. A heater alone is not enough. If you put a heater in a large tank of still water, the water right next to the heater will be hot, while the water in the far corners will be cold. This is called thermal stratification. What it does, the curing tank circulator is the partner to the heater. It prevents hot and cold spots. How it works, it acts as an underwater turbine, continuously agitating and churning the water throughout the entire tank. Why you need it? By constantly moving the water, the circulator ensures a completely uniform temperature distribution. This guarantees that a test cylinder sitting in the back left corner of the tank experiences the exact same curing environment as a cylinder sitting in the front right corner. It ensures consistency and repeatability, which are the hallmarks of good science. Moisture Room Control Panel. Finally, some labs prefer not to use water tanks. Instead, they build entire moisture rooms or fog rooms, sealed chambers where thousands of cylinders can be stored on racks. But maintaining a room at 100% relative humidity without it raining inside is an engineering marvel. What it does: the moisture room control panel is the brain of a professional curing facility. It is a centralized command station that manages both the temperature and the atomized water output of the entire room. How it works: it hooks directly into the lab's water supply and electrical grid. The panel monitors highly sensitive humidity and temperature probes located inside the fog room. If the humidity drops to 98%, the panel instantly triggers the atomizer nozzles, filling the air with a microscopic water vapor that stays suspended in the air, preventing the cylinders from drying out. Why you need it? It allows testing laboratories to scale up massively. Instead of managing a dozen separate water tanks, a lab manager can look at this single control panel and instantly verify that every single piece of concrete in their facility is curing in absolute ASTM-compliant perfection. Concrete is not just dirt and water. It is a highly engineered chemical composite, and it demands respect. The strength difference between properly cured and improperly cured concrete is not an estimation. It is a measurable, physical reality. When you allow water to flash evaporate, you rob the cement of its ability to bind the matrix together. You introduce microfractures, you increase permeability, and you drastically reduce the lifespan of the structure. Whether you are pouring a backyard patio or a structural column for a suspension bridge, the rules of chemistry do not change. To prove that a structure is safe, testing laboratories rely on uncompromised data, and uncompromised data requires uncompromised samples. If you are a professional in the construction or materials testing industry, you cannot afford to guess when it comes to quality control. You need the right gear for the job. You can find all of the specialized curing boxes, tank heaters, and laboratory equipment we talked about today by checking out the links below. Thank you for joining us on this deep dive into the hidden science of concrete curing. We hope this clears up the drying versus curing myth once and for all, and helps you understand why precise temperature and moisture control is the secret to building structures that last. Subscribe and like this video. For more professional materials testing equipment and industry insights, visit us at our channel.